Okay, dear, I'm starting the class. It's already too late, 8:17 time. Okay. Um, Today, inshallah, I'll finish this chapter 5. After finish this chapter 5, if time is there, I'll start your chapter 6 also. Okay. From next week, your assessments and discussions in the blackboard itself. Okay. First, coming to the chapter 5. So this chapter 5 is related to two-dimensional viewing. Okay, so two-dimensional viewing means like displaying and like seeing, like as an output. Okay, so by using the two dimensionals, how we can show the outputs according to your planes. Okay, so see here first, coming to the first one, clipping. Clipping is nothing but a like extracting and identifying the element of a scene or picture or outside a special region. It is called as a clipping region. Okay, so normally in the computer we can say that control X, control C, control V, like that. No, cut the information and paste into some other slide, like that. So that procedure is called as clipping. So if you have a more information, suppose you want to get only 2 lines or 3 lines, you want to extract, so that time you can use this procedure. So which reason you want to give as a special output, that reason you can cut like this and paste into another slide or another place. Okay, so this cutting reason is called as a clipping reason. Okay, and procedure of doing like this is called as a clipping. Okay, so normally this clipping can be used for copying, moving and deleting a portion of the scene or picture. Okay, so normally this clipping procedure can be useful for whichever you want, whatever you want, that information you can make as a copy, or you can make as a moving, or you can make as a delete from the entire portion, of your information. So see here, normally they gave example, the classical example, cut and paste. Normally we know that, right? So cut this region. For example, this is entire picture. So if you want only this portion means you can cut this portion and come to another place. Here you can paste, here you can paste that portion. So this procedure is called as a clipping procedure. Okay, then coming to the example of clipping window. See here, this is a clipping window. So now you can understand, I think. See this one. See, by seeing this is a x direction, right? This is x plane and this is y plane. Okay, so in this x and y plane we have some image like this. This is image. Okay, so this is image, but I want only this portion. So this portion means you can cut this portion, selected portion. Okay, so you can paste this portion out of this window. So see here, yeah, so this one. So this is called as a clipping window, and also we can indicate this is nothing but a output, and also we can say this is nothing but a viewport. Okay, so let me discuss first how to make the clipping window. Okay, see here, normally using the section of two-dimensional scene that is selected for display is called as a clipping window. That means using like this x direction and y direction. Suppose here you have the image like this. Here you have image like this, but you want to select a section what you want to clip. So for that, suppose I want to clip only head with hands. So this portion I can cut. So this portion is called as a clipping window. Okay, this portion I can cut here, and after cutting this portion, I can copy this portion and I can paste into some other x and y plane here like this. This is called as a viewport, like that output. Okay, so your input is full picture, full information, but here output is what we want to see, what we need to paste. So that is called as a output. So and also this is called as a viewport in our graphical manner. Okay, so see here, discussion about the viewport. First, the objects inside the clipping window are mapped to the viewport, and it is the viewport that is then positioned within the display window. Yeah, so this cutting portion we can paste throughout the x and y direction plane. Okay, same like that before we saw, right? The before full picture also it is present in the x and y plane only, but here also the cutting portion also what we want to see, that portion also, that window also we can say in the, we can save in the x and y plane. Okay, so this viewport portion can be viewed in the output devices. Okay, so this one like this. Okay, then coming to, yeah, see, this is the example of modeling coordination, world coordination, viewing and project coordination, normalized coordination, and device. So how modeling coordination? So inside the modeling coordination, what is there? So modeling means everyone understand that it is a structure, it is a design. Okay, so inside the modeling coordination, what we will do, construct world. You can use a coordinate, you can use a full scene, and you can use a modeling coordinate, and you can use some transformations. So in the modeling coordinates, so you can transfer this modeling coordinates to the world coordinates. Here MC means modeling coordinate, WC means world coordinates, VC means viewing and projection coordinates, and NC means normalized coordinates, and DC means devised coordinates. So this picture can show that two-dimensional viewing transformation. Okay, so two-dimensional, here see this one, two-dimensional viewing transformation pipeline. So whatever the image, whatever the scene, whatever the picture you represent using the x coordinate and y coordinate plane, that can be showed like this. Okay, so see here, first in the modeling coordination we will do all these things. Then coming to the world coordination, inside the world coordination, yeah, construct the world coordinate to view the coordinates what you want to see. Okay, so that coordinates you can transform viewing coordinate to normalized coordinate. Suppose this is a full picture, it is present here. Okay, so full picture it is present here, but here whatever you want to see, that you can transfer to here, this one. So suppose only head like this. Okay, after that you can transfer this viewing coordinate to the normalized coordinate to display in the devices. So you can transfer this to here to display in the output devices, in the output devices. So this is the procedure for displaying, viewing two-dimensional transformations of any pictures, any scenes using the pipeline. So this is a pipeline, we can say this is a pipeline to display two-dimensional viewing. Okay, So this is very simple. So you can draw first modeling coordinates, then you can draw here world coordinates, then you can make it as a viewing and projection, then you can transfer to the normalization coordinates. After that you can transfer to devices to display the output. Okay, so see here in the device coordination, video, we can see video monitoring and plotter using the x and y plane, and like another output only picture like that. Okay, so here we have a different devices to display the outputs. So you can write all these different devices inside the device coordinates. Okay, then yeah, normalization and viewport transformations. So let me discuss what is a normalized transformations and what is a viewport transformations. So see here, normally many of the applications, it can combine the normalization and window to viewport transformations. So normally window to viewport transformation, so many applications we can see in our graphics. Okay, so first the coordinates of the viewport are given into the range 0 1, so that viewport is positioned within the unit square. So that means which portion you want to show as a viewport. For that you can give some range. So you can give some range like a 0 1 0 5, whatever it is, you can give some range. So in that range viewport will be present, viewport will be positioned inside that unit square. Okay, then after clipping, the unit square viewport is mapped to the output devices. So after that, first here this one is the full of your picture, it is present in the x and y coordinate planes. So inside this x and coordinate planes, whichever you want to show as an output, for that you can give some unit square. So inside that unit square your output will be present. So that output port is called, that output we can say it is a viewport. Okay, so that viewport you can map it to any output device to display the your cutting portion. Okay, then in another systems, normally the normalization and clipping is performed before viewport transformation. Yes, obviously. So first we can say that it is a normalized picture. So in this normalized picture we want to perform some clipping like this, some clipping. So after clipping we can say this is called as a viewport. This is the procedure of this one. In another systems, normalization and clipping can be performed before viewport transformations. Okay, then coming to the next point, viewport boundaries are given in the screen coordinates relative to the display window position. Yes, of course, whatever the viewport you make the clipping, that can be displayed in the window position. So like this, here maybe 0 to 1 like this, 0 to 1 in X plane, 0 to 1 in X plane, and here maybe this is 1 to 2 in Y plane. So like within this position, within this display position, your viewport will be present. Okay, so this two is called as a boundaries. This two is called as a boundaries of your screen. Okay, then yeah, mapping the clipping window into normalized viewport. Okay, so just imagine that if you have a very big picture like this, very big picture, this is your very big picture you have, you want to cut only this portion till here, you want to cut only this portion. So after cutting this portion, if you want to show this portion as a full of your screen, okay, that procedure is called as a mapping the clipping window into a normalized viewport. It cannot show like a small image, like a big image. It can show as a normalized image after cutting the position, also after cutting the, yes, after cutting the window also it can show the full of your screen. So for that, what is the procedure? First, description object descriptions are transferred to this normalized space using the transformations that maintains the same relative placement of point in the viewport it had in the clipping window. Yes, so that means first whatever the clipping window you made, that clipping window automatically transformed to the same placement of the viewport in the display device. Okay, and also coordinate position at the center of the clipping window, for example map to the center of the viewport. Suppose you cut this portion in the x plane and y plane. If you paste this portion in another another coordinate position in the same place itself, it can show like this. In the same place itself it can show like this, center of the viewport. And for that you have to make the position of your window and the position of your viewport. So if you make these two coordinates like a boundaries of your x and y coordinates, the associated viewport can be displayed in the center of x and y coordinate plane. Okay, here we can obtain the transformation from the world coordinate to viewport coordinates with the sequences. Okay, so before we discussed, right, two-dimensional viewing. So in that two-dimensional viewing pipeline, first we made a model. After that we can convert that to world coordinates. After that, that world coordinates can transform to viewport coordinates. So this is actual procedure to map your clipping window to the normalized window. Okay, yeah, see here example they gave. First, scale the clipping window to the size of viewport using the fixed point position. Okay, so the what is the fixed point position is, see here, x window minimum, y window minimum. This is the fixed point position. Okay, so in the x and y plane you make first minimum position, fixed point position, what you want to make as a clipping window. Then the second point is translate this window minimum position to viewport minimum position. Okay, so remember girls, this is a window minimum position. Okay, you can translate this window minimum position to viewport minimum position. So this one, this is your window minimum position and this is your viewport minimum position. Okay, so how can you translate? See this one. Yeah, yes, see here, this is viewport position. So same like this only, you can replace instead of window position to viewport position. Okay, so this is viewport minimum position and viewport maximum position, and viewport minimum position and viewport maximum position using the viewport coordinates, viewport and project coordinates. Okay, so this is the step 3. First you can size your scale, then you can translate window minimum position to viewport minimum and maximum positions. Then yeah, see here, then to transform the world coordinate point into the same position within the viewport. So already we made, so this no need, yeah, this no need, just read this point enough. Okay, okay, that's all. Then coming to the clipping algorithms. So here clipping algorithms. Remember girls, clipping means normally in the computer language we can say that cutting. Okay, cut the portion, cut the region what you want. So for that, here in the graphics we have some different algorithms, clipping algorithms. So here see first one, using the point we can make the clipping, using the line we can make the clipping, and using fill area we can make the clipping, and using the curve we can make the clipping, and also using the text we can make the clipping. So these are the different clipping algorithms we have in our graphics: point clipping algorithm, line clipping algorithm, fill area clipping algorithm, curve clipping algorithm, text clipping algorithm. So these are the different clipping algorithms we have. Okay, let me discuss each and everything. Yes, first two-dimensional point clipping algorithm. Okay, see here, this is the condition you have to remember very clearly. So what is the condition we have to satisfy to perform the two-dimensional point clipping? Means x minimum is less than or equal to the point is less than or equal to x maximum. That means in between the minimum and maximum you can choose one point like this. Suppose this is minimum and this is maximum. So in between these two, minimum of x coordinate, maximum of x coordinate, you can make one point. This point is called as x. So same like that you can make in y coordinate also. The minimum, in between the minimum and maximum you can choose the same another point. We can say this is x and y point. See here, this one. Using this procedure you can perform the point clipping algorithm. Okay, and this one, for inequalities is not satisfied, the point is clipped. So for example, if you didn't made the point like this in between the minimum and maximum of x and y coordinates, so suppose this minimum and maximum points are inequalities, you cannot make the point clipping. Okay, so that is another important point for this two-dimensional point clipping. Okay, then point clipping is applied less often than line or point polygon clipping. That means point clipping we cannot use so many times because need compulsory the minimum and maximum positions are very clear and equal boundaries. If that equal boundaries are not satisfied, your point clipping algorithm cannot work. So why we are saying that point clipping can be used very less compared to the line and polygon clipping algorithms. Okay, and 1 minute. Okay, then coming to the next one. Yeah, see, this is example of point clipping. Okay, so in between the maximum and minimum, here minimum and maximum we choose the point. So because of equal boundaries, this is also example 0 1, this is also example 0 1. So in between the 0 1 and 0 1 you made the point very clearly, so this is called as a point. Okay, then two-dimensional line clipping algorithm. So already you know that to make the line you need 2 points, right? Point 1 and point 2. That means 2x x1 y1 and x2 y2. Okay, see, if you want to perform two-dimensional line clipping algorithm, you have to make the 2 points. First one is x1 y1 and the second one is x2 y2. Using these two points you can perform the clipping line clipping algorithm. See here example they made that before clipping this one. So before clipping, see, this is a boundary. Okay, this is the boundary. Okay, so we want to perform clipping on this boundary using these line clippings lines. So point 1, point 8 is one line, point 3, point 4 is one line, point 5 and point 6 is one line, like this. By using these points you have to perform the line clipping algorithm. So after clipping algorithm, see, this is your output. So inside the boundaries the lines will be present. So whatever the lines is present outside the boundary, that we made clip, that means that we made removed, like this. See, like this. See this one. So this is your line clipping algorithm example. So remember girls, if you want to perform the line clipping algorithm, remember the important point, whatever the lines is present inside the boundary, that can show in the output. So you made one boundary. So see, for example, this is your boundary. So inside this boundary is your output. Okay, then yeah, here see, this is the explanation of line clipping algorithm. So with both endpoints of line segments are inside of your boundary, that lines can be showed as a output. Okay, so same thing, whatever here I explained, this one, okay. So if you want to make a clipping means like this, you can make one boundary. So whatever the lines is present inside the boundary, that is your output while after performing your line clipping algorithm. Okay, then Cohen-Sutherland line clipping algorithm. Okay, next, coming to the next algorithm, Cohen-Sutherland two-dimensional line clipping algorithm. So normally in the line clipping algorithm, we have, I think, two different types of line algorithms, I think. Yeah, normal line clipping algorithm and Cohen-Sutherland line clipping algorithm. Okay, so see here in the Cohen-Sutherland line clipping algorithm, first what you want to do is you can divide the clipping region into number of sections, like this, especially 9 regions, like this. One, see, this is 1, 2, 3, this is 4, 5, 6, 7, 8, 9. Okay, so whatever the clipping you want to perform, whatever the picture, whatever the portion you want to make the clipping region, first point is you can divide that clipping region into number of sections. Mainly we have to divide into the 9 regions, like this. Okay, so 9 regions you can divide your position of your picture. After that, each line endpoint is assigned with its own 4-bit binary number called an out code or region code. Okay, after dividing your portion into the 9 regions, for each and every region you can assign a unique code that can called as a region code. So like this, here see this one, 10010001 binary values. Okay, so you can assign the binary 4-digit binary values for each and every region. Okay, after that, each bit position is used to indicate whether the point is inside the clipping window or outside the clipping window. So by using these 4-bit code, we can identify which is present inside the clipping window, which is present outside the clipping window. Okay, so after making that, see this one, bit 1, bit 2, bit 3, bit 4, and also you can make the boundaries. So like this, this is bit 1, for example I am telling, this is bit 1 and this is bit 2 and this is bit 3 and this is bit 4. So for the clipping windows compulsory we have the 4 boundaries, right? So top and bottom and right and left, we need a 4 boundaries. That also you have to make a very clearly using the 4-bit code, like this, bit 1, bit 2, bit 3, bit 4. So you can make the bit regions, bit boundaries of your clipping window. Okay, after making this, yeah, then using that possible bit positions from 1 to 4, from right to left or from top to bottom, you can perform the clipping. Okay, so by using the bit regions, you can make the clipping window and you can transform to that viewport window. Okay, so this is the procedure of your Cohen-Sutherland line clipping algorithm. Okay, then coming to polygon clipping algorithm. Okay, so polygon clipping algorithm, I think everyone knows that polygon means you have a 5 edges, right? So see, for example, this is polygon. Here polygon will be present like this, right? 5 edges. This is 1, this is 2, and this is 3, the 4 and 5. So 5 edges will be present in the polygon. So by using the polygon clipping, first what you want to do is, if you have a closed polygon, is clipped as a collection of lines within the line. So normally we can define the polygon is a collection of lines. So see here, 1 to 2 there is a one line, 1 to 3 there is a one line, here 2 to 5 there is a one line, 4 to 5 there is a one line. So normally we can say polygon is a collection of lines. So you can think maybe this is also like a line clipping algorithm, but we can use, instead of line clipping algorithm, by using the polygon clipping, we can perform inside the closed polygon and outside the closed polygon. So you can make the clipping inside the closed polygon and also outside the closed polygon. So normally this polygon clipping algorithm can become, see this one, this is the original closed polygon becomes one or more open polygon or discrete lines. Okay, so if you make a clipping on this polygon, maybe output is closed polygon or maybe it is a open polygon. So here they gave one example, see this one. Yeah, see this one is a polygon algorithm example. So before it is a closed, this is full inside, see this one, before it is a closed loop, closed polygon. After performing the clipping algorithm, this is open, see this is one line and this is one line, there is no closed, it becomes the open polygon. Okay, so this is example of your polygon clipping algorithm. Then here another example. So how to perform this one, when if you consider polygon as a closed and solid area, after performing the clipping, maybe sometimes it is closed, maybe sometimes it is open. So this is one of the main example to perform using the closed polygon. Okay, so for example, see this one. First you have to assign the, what it is called, you have to assign the names of your edges. So for example, I make the assigns of examples like this, see here, like A, B, C, D, E, F, G, H. Okay, see here you can perform the clipping algorithm by making the lines. So A to H, one, sorry, this one, A to Z there is one line, B to C there is one line, E to F there is one line, I to N there is one line. So first you want to make which lines you want to perform the clipping. After that you can perform the polygon, you can implement the polygon clipping algorithm. Okay, so this is a one of another example, big example, this one same before what I teach, same example, but here you are assigning a names like A, B, C, D, like that. After performing the clipping algorithm, you are assigning the lines, which lines you are going to clipped, and maybe this polygon is closed or not. To identify, you are making this lines, you are assigning the names of these lines. Okay, then next algorithm is Sutherland-Hodgman polygon clipping algorithm. Okay, first one is normal clipping polygon clipping algorithm, but here Sutherland-Hodgman clipping algorithm. So normally this Sutherland-Hodgman polygon clipping algorithm can be clipped by processing its boundaries. Okay, by processing its boundaries. Okay, then using the boundaries we have to perform the clipping. That procedure is called as a Sutherland-Hodgman polygon clipping algorithm. So see here, first consider an example. See, first step, you have to perform only the left side. Then the second step, you can perform, see this one, where is that? Left clipped. So delete this one. And the third one, you can perform the right clipped. And the fourth one, you can perform the top clipped. And the fifth one, you can perform the bottom clipped. That means we have to use the boundaries like a top, left, right, and bottom. Like that you can make the step by step clipping of the polygon or clipping of the any image. Okay, so this is the procedure of Sutherland-Hodgman clipping algorithm. By considering the boundaries of your image, we have to make the clipping. First step, not all boundaries together we cannot make the clip. So first you can make one side, then you can make another side, then you can make another side till complete the boundaries. We have the 4 boundaries only for each and every window, right? So top boundary, left boundary, right boundary, and bottom boundary. So you need to make compulsory 4 steps. Okay, so this is the first step, second step, third step, fourth step, and fifth step. In the first step, you have a original diagram. In the second step, maybe left. In the third step, maybe right. In the fourth step, maybe top. In the fifth step, you can make a bottom clipping. So this is your actual Sutherland-Hodgman processing steps. Okay, then coming to this is the explanation of your Sutherland-Hodgman or this example explanation. Okay, so this example explanation, what is the first step, what is the second step, this each and everything here we explained clearly. Okay girls, this is your fifth chapter finished. Okay, now we can start chapter 6 also. Okay, inshallah today we will finish the syllabus. Okay, so from the next week I can start your mid-exam and discussions and assignments, everything in the blackboard itself, using the discussion board and using the online exams. Like that I will make for your completion of full 100 mark. Okay girls, for everything I will make here in the online itself. I hope you got the information already, right? Okay, then go for the next chapter, that is chapter 7. Sorry, 6, chapter 6. Chapter 5 was finished. Now I can share the chapter 6, 3-dimensional viewing. Now coming to chapter 6. Okay. First coming to this chapter 6, this is the 3-dimensional viewing. Till now we discussed about only using the 2-dimensional viewing, only using the x and y coordinates, how to display your portion, how to display the images, how to make the boundaries. All these things we will discuss in the chapter 4 chapter 5 in the 2-dimensional viewing. Okay, now we can go for the 3-dimensional viewing. Okay, first so 3-dimensional viewing concept. First of all, we have to understand that what is the 3-dimensional viewing concept. Okay, so first point, so it is the field of computer graphics that deals with generating and displaying 3-dimensional objects in a 2-dimensional space. Okay, so we are displaying the three-dimensional objects, but the two-dimensional objects are three-dimensional objects are displaying in the two-dimensional space, like a monitor, like a screen, like that. Okay, and the second point, in addition to color and brightness, a three-dimensional pixels adds the depth property that indicates where the point lies on the imaginary z-axis. Normally, to display the three-dimensional objects, we can use the three-dimensional pixel color and brightness. That means including the three colors, right? Red, green, blue, three colors, three dimensionals pixels we can add to our objects to display very clearly where the point is present, where the point lies on the imaginary z-axis, everything we can use in the three-dimensional viewing. Okay, when many three-dimensional pixels are combined, each with its own depth value, the result is three-dimensional surface. It is called as a texture. Okay, so here many three-dimensional pixels are combined, like more red color, more green color, more blue color pixels are combined. That time it will show three-dimensional surface. Each and every three pixel clear value it can show on the three-dimensional surface. Whatever the value it is showing, whatever the result it is showing on the three-dimensional surface, it is called as a texture. Okay, see this one, it is called as a texture. Okay, this is the definition of texture. Okay, then objects are created on the three-dimensional stage where the current view is derived from the camera and light sources similar to the real world. Yes, this we know that. So the three-dimensional objects looks like real objects, real world objects. The three-dimensional objects are created by using the cameras, or using the light sources, or using holograms. Like this we have to create a three-dimensional objects. Okay, then yeah, see this is example of three-dimensional objects. So in the three-dimensional objects, everyone has to remember we have three directions with 360-degree angle. Okay, so this is x direction, y direction and z direction. With 360-degree angle we can view the concepts of three-dimensional objects. Okay, then yeah, three-dimensional display methods. How many types of display methods we have to display? We have to show three-dimensional objects. So first one, parallel projection, and the second one, perspective projection, and the third one, visible line and surface identification, and the fourth one, depth cueing. Okay, so let me discuss each and every type of projection, method of projections. First, coming to the parallel projection. First one is parallel projection. So see here, in the parallel projection, project points on the object surface along parallel lines onto the display plane. Yeah, see this is, everyone knows that parallel means here one object is there and here one object is there. The two objects we can display in the same time. Okay, parallel lines are still parallel after projection also. That means you can display like this objects. This is one object and this is another object. You can display the both objects in the display plane in the same time. Normally this parallel projection can be used in the engineering and architectural drawings. Okay, to make the house, three-dimensional house, and to make the three-dimensional road, to measure anything. Okay, in the engineering, in architectural drawings, we can use normally this parallel projection. Okay, then coming to the perspective projection. So here see this one, perspective projection means these projected points to display the plane along converging paths. That means this is the way that our eyes and camera lens form images, and so the displays are more realistic. One minute. Okay, so here parallel projections can show just dimensions of your parallel objects, but here the perspective projection can show objects as a very realistic objects, so more realistic objects. Okay, so we can feel that this is a very realistic object. By using this perspective projection we can display that type of three-dimensional objects. Then coming to visible line and surface identification. Okay, so mainly in this method, visible line and surface identification method, it can highlight the visible lines. Okay, it can highlight the visible lines, or it can display in the different colors. That means only the outline colors. Outline colors, maybe it is in the bold color, or maybe we can have a special categorization of this dashed lines colors. One minute, ma. Wait 1 minute. Okay, so here in the visible line and surface identification, only we can show the special kind of lines that will be in the highlight format, or that will be in the different colors, or that will be in the dashed lines, some special categorization lines. Okay, then coming to depth queuing objects. So another one is depth queuing objects. These depth queuing objects, we can easily identify the front and back of your display object. That means in the 360-degree angle we can saw that object. So that type of objects can be displayed by using this method. Okay, so in this method the objects has a very depth information, and that objects can be made by using the various methods to show very clearly, like a front to back and inside and outside, whatever it is. Okay, that type of objects can be showed by using this depth queuing method. Okay, then coming to example of parallel projection. See, this is the combination of lines. This is one object, this is one object, this is one object, this is one object. Like this we can show our objects in the parallel projection. Then properties of parallel projection. So these properties, first you have to remember, in the parallel projection the objects cannot see as a real objects, just it looks like a combination of lines. The objects are not realistic looking. Okay, then and it is very good for exact measurements. So because of the lines, the combination of lines, we can measure very clearly how much distance it is there and how much long it is there. Like that we can measure exact value. And this parallel lines, see, this is an important point. So after projection also the parallel lines looks like a parallel only. It cannot delete it, or it cannot hide, it cannot integrate. Okay, so after projection also the parallel lines are remains parallel only. Okay, and we can make the calculations ratios very clearly. Okay, and also angles are often not preserved. Okay, so this parallel projection can be used mostly in the architectural drawings, and also to design any computer aided designs, and exact measurements whatever you want to make, you can use this parallel projection method. Okay, then coming to Perspective projection. See, this is example of perspective projection. We can feel that this is a very real object, but this is not a real object, right? This is like a diagrammatical object, but we can feel that this is a perspective projections has a two categories, two characteristics. Okay, so what is the first character? Smaller as their distance from the observer increases. This is first characters. It look like a smaller in the distance, but it can increases the value or increases the size of the objects while seeing that three-dimensional object automatically. Okay, and another characteristic is four short end. So that means the size of your object dimensions along the line of seeing are relatively very short. The dimensions we cannot calculate very clearly. Okay, that is another characteristics of perspective projection. Okay, and coming to the properties of perspective projection. Yeah, properties of perspective projection. This is an example of projective transformation. So suppose you have any one object like a three-dimensional object, but that is not a real object. Suppose you want to transform that object to realistic object, you can use the perspective projection. Okay, so lines after projection, it cannot remain the same. Maybe it can combine, or maybe it can integrate, like that it can display in the projection. And another important point here, the parallel lines. Suppose in your object there is a parallel lines, it cannot show after projection same lines. Maybe it can combine, maybe it can delete, like that it can show in the projection. Okay, and main advantage of this perspective projection is that size varies inversely proportional to the distance, looks realistic. That means like a three-dimensional movie. So sometimes it can show, you know that virtual reality glasses is there. Suppose if you wear the glasses, you can see the size is exact size. Suppose you can remove the glasses and you can see that three-dimensional object, its size will be different. That means the size will be vary depending on the distance looks. Okay, then coming to 3D viewing pipeline procedure. Same like that two-dimensional viewing pipeline also. Here we can say first you can construct the modeling, then you can transform to the world coordinates, then you can transform to the viewing and projection coordinates, then you can transform to the normalized coordinates. After making the normalized coordinates projection, you can transfer that three-dimensional objects to the device coordinates to display your output. The same procedure here also. Okay, then yeah, here you can remember girls from the slide number 11, from the slide number 11 to 19. Girls, remember from slide number 11 to 19, you can delete the slides because these are all calculations you cannot do here. Okay, so you can delete the slide from 11 to 19, 9 slides. Okay, girls, slide number 11 to 19, remove please. Okay, then coming to transformation. Already in the chapter 4 also this concept came. So transforming but in the chapter 4 the transformation means from one object to another object, and by using the scale object to another scale object, like that we can make. But here in the three-dimensional viewing transformation, we are going to transform two-dimensional objects to three-dimensional objects using three coordinates. So first in the two-dimensional coordinates we have only x and y coordinates and the window size, but in the three-dimensional coordinates we have x and y and z coordinate along with the window position. So By using this concept, we can transform our two-dimensional objects to three-dimensional objects. Okay. Yeah, see, this is the procedure how we can transform your three-dimensional objects to a matrix multiplication and two-dimensional objects to your three-dimensional objects, all these things. Okay, these 4 steps. Okay, girls, thank you. Your